So as you mentioned, I'm Margarita Castro. I'm a postdoctoral fellow here at the TAL. And I'm going to share with you one of the projects that we have been working on that is incorporating service reliability on multi-depot vehicle scheduling. So in this project is basically how we can use data analysis and all the data that we have available nowadays to make smarter decisions and actually achieve the goals that we want. Oops, okay. So first I want to talk a little bit about the vehicle scheduling, just to give you a brief overview of what the problem more or less. So this is a very common problem in public transit agencies. Basically what you want to do is that you have a timetable of trips. Basically a trip is you want the bus to go from a start station to an end station. It has some departure times, a route. So it's basically a schedule of how the buses are going to behave. But the vehicle scheduling problem, what it actually does is that we want to assign the buses to these timetable trips. So the main idea is that, for instance, each bus will have a sequence of trips that they have to execute. And the main idea, the main objective here is to optimize the schedule. So we want to minimize the fleet and all the operational costs associated with this problem. So this is the most basic problem. Actually, in our problem, we're going to work with slightly more complicated where we have multiple depots. So basically, we have depots that have limited capacity. So basically, the number of buses that are stationed in each depot. We have the trips the same as before, and also some operational costs. And we can see the problem using this network flow model. So basically, we have the depots, we have the set of trips that we want to execute, and the arrows basically say if they can be connected one to the other one. And the main idea, as I said before, is that we want to assign trips to exactly one bus. So for instance, this violet bus has trip 1, 3, and 5. And we wanted to start and end at the same depot. So if I start at depot 1, I have to end at the same depot. And as I said before, minimizing the cost is the main goal. But the issue here is that usually how people solve these problems in practice and even in research is using a deterministic case. When I say deterministic case, what I mean is that we consider that the traveling times are always the same. There might be maybe the average traveling times or some estimation of the traveling times. But these usually are very misleading because we're ignoring traffic or weather or any other thing that can give us some delays. So there are several issues when we try to find a good vehicle schedule when we consider just deterministic data. So for example, one thing that you can do is if you're using deterministic data, it's like, okay, let's say that the traveling times is just the average times that we have observed throughout the operation. And the main issue is that the schedule might be feasible on average, it might look very good, but this is sensitive to delays in practice. So this can have a lot of complications during practice. You might have trips that are always delayed. So it's not usually very good. And the other thing that usually people actually do in practice is knowing that the average times are not very good, they use over approximation. So we say, okay, the average time is, I don't know, 10, but I'm going to over approximate it to 15, have a little bit of a slack to make sure that I don't have that many delays. But the problem here is, well, how much do I overestimate? That's one of the main questions. And the other problem is that if you overestimate too much, then you will have skills that have high costs. Maybe you will require more buses that you actually need. And there's no guarantee that you're actually going to have an acceptable on-time performance, so that you're basically having less delays that the passengers will observe. And this is something that a lot of people in the research community have explored, how to consider the stochasticity that is inside these traveling times. So one thing that you can consider is, for instance, penalizing the expected delays. But the problem with this approach is that we basically ignore the propagation of delay. What happened if the trip that we had before was delayed? How that affect the next trip that the bus has to do? Other option is rescheduling or real-time vehicle scheduling. So in these cases, you have to make adjustments during the operation to feature scale depending of the delays that you're observing. But they're usually not very easy to apply in practice because you need some sort of like a person telling the drivers, okay, now change this, you're not going to do this trip, you're going to do this other one because you're late, or and you basically have to synchronize and make a lot of more decisions and make the execution much harder. And one of the main reasons why this is so important is because of service reliability. And this is one of the main measures of how we, main measures to see how good is our schedule or not. So this is just a picture that I took from the TTC, where it basically shows the service reliability target that they want, that is 95%. So this means 95% of the services or the trips have a departure time in a reasonable time window. But actually what happens, and I'm pretty sure if you look at it today in the TTC, you will see that it's not achieved. It's always a little bit less than their target of 90%. So what we want to do in this project is to try to incorporate the service reliability when we construct these vehicle schedules. And so what we want to do is build cost-efficient vehicle schedules, but also guarantee this on-time performance, or OTP, during the days of the operations. And here is where we use a technique called stochastic optimization models, where we're basically going to combine optimization techniques with some data analytics. So just to give you a brief overview of what's the methodology, to not go to all the details, what we're going to do is optimize over a set of scenarios. So basically what I'm saying is that instead of considering average time or over approximations, we're going to consider a large set of scenarios and make sure that our scale is good for at least 95% of these. So we want 95% of the scenarios to achieve the target OTP that, for instance, in the case of the TTC, as we see in the webpage, it was 90% of the buses are no more than 5 minutes late for each of the trips that they had to perform. And to model this, we use what is called probabilistic constraints. Another key feature of this problem, which actually makes it quite challenging, is that we have integer variable or discrete decisions. So basically we have to assign trips to depots and to buses. We need to be counting how many trips are delayed for each scenario, and also the number of scenarios that meet the OTP target. So to solve this problem, just to give you a quick overview of more or less how it's solved, it's basically an iterative procedure where we're going to build schedules, evaluate them, and try to get some feedback from them. So we have a first model that creates a schedule. We can start, for instance, using just average times. Then once we have the schedule, we evaluate it over our set of scenarios that we generated, and this is basically generated from real data. And then after the evaluation, we see if there's some parts of the schedule that are giving us too much delay and we're not achieving our OTP. So we give some feedback back to our scheduler to give us another schedule that hopefully correct these issues. So we do this over and over again until we finally found a schedule that has the OTP that we wanted in at least 95% of the scenarios. And the interesting part of here is if we see actually the results, it does everything, like all the things that I told you that doesn't make sense. Is it worth it? So I have some small preliminary results on some synthetic data that we did. I have instances with 75 or 100 trips, so they're very small, but we will see how it works here. Number of depots, 2, 3, or 4. We have 5 random instances per configuration. We solved this using 200 scenarios, so not too big. And then we evaluated over 1,000 other scenarios that we sampled. And here are more or less the results. So I'm going to explain it very briefly. So we wanted to compare what happens with the deterministic model. So if we use just average times, then we have the deterministic by the plus standard deviation. So we're basically creating a scale where we over approximate the times a little bit for each possible trip. And then we have our stochastic approach. So in the first part of the table, we have the average cost increase. So with respect to the deterministic model, how much costly is the scale that it gives us these techniques. And we can see that if we use a very standard over approximation, the costs are much larger than if we use the stochastic programming approach that I was mentioning, this iterative building the scale. And more surprisingly is the on-time performance. So here is how many scenarios actually achieve on-time performance. And we can see that the deterministic case, very similar to what we actually see in practice, is like more or less 50% of the times we have achieved the OTP. If we have some over approximations, of course, we do better, but it's very, it kind of like varies. There's a lot of variance here. It could be 70%, 77 or 91%. And our stochastic programming model, even though it was just optimized over 200 scenarios and not that many, it was giving us very reliable on-time number of scenarios in evaluation that have good on-time performance. So always, all of these are above 85% and usually close to 90%. So it's pretty good and much more reliable than just using this more deterministic or heuristic type of procedures. And in terms of real world data, what we're analyzing now, actually working on it, is a study case for Halifax. So in this case, we have a problem that is much larger. We have 2 depots, which more or less consists of 300 buses that we have available. They have 70 different routes for their buses and around 4,000 trips. So we have done a lot of like data processing, especially for the period of winter 2019, to try to see how the behavior of the trip durations and how we can estimate these values so that we can sample and create our scenarios for optimization model. So we use for the trip durations the GTFS data that is available, free, available for everybody. We have noticed trying to fit different distributions, that log normal distribution were the ones that were behaving better and predicting better they were fitting better the data for the different trips. So here I have like 2 examples of how this looks like. And also we needed to estimate the deadhead trips, the deadhead travel time between the trips. And here we were using the here data that basically tells us how much time, how is the traveling time, either it's a bus or a vehicle or any type of motorized vehicle between 2 points in a city. So we are all basically using different sources of data to estimate the different traveling times that we have in our problem. So now,
Margarita, about a minute left.
Okay, almost done. So just to finalize, overall, we have proposed a stochastic variant of the multi-depot vehicle scale that considers service reliability. We developed this iterative algorithm to solve the problem over a large set of scenarios. And as I showed with my preliminary results, we have showed the value of this stochastic model and how actually you can make smarter and better decisions. And in terms of a study case, we still have some things to do. So for now, we have analyzed the traveling data for Halifax. Now we're in the process of building the scenarios and solving the stochastic model, and then evaluate the resulting scale. So that's it for me. Thank you very much for listening. And I want to thank our partners, Trapeze, that have helped us with our study case. And this was also thanks to my Text Accelerate program.